Joe Stiglitz in JABO, the Journal of Economic Behavior and Organization. I think that's the name. And he also has publications in JDC and other top journals. So I thought when I saw Corrado's latest paper on COVID-19, I thought it would be a good idea to try to organize a joint seminar, because COVID-19 is everywhere, and so it's good to also see some research on this topic. So I hand over to you, Corrado. Thanks for accepting our invitation, and we're looking forward to your presentation.
Okay, thank you, Dirk. So I'll share my screen. I hope there are no issues. Okay. Okay, thank you for the invitation. Thank you for the kind introduction, Dirk. It's a pity I cannot be there, but the paper is on COVID, so if it wasn't for COVID, there wouldn't be a paper. So I guess it's okay given the circumstances. So this paper is a joint collaboration with my fellow economist Georgios Galanis, who is at Goldsmiths, University of London. And we've been working together for a little while on sort of behavioral macroeconomic type of models. And then for this project, we involved the only person who actually knows something about this type of issue, which is Dr. Bascosos, who is not, and is a bioinformatic. So he has knowledge a little bit more than us about epidemiology, and also he helped us with the estimation. If you read the paper, if you see the paper, probably you realize nowadays it's a bit outdated, in the sense that we started working on this a few weeks ago, more than a month ago, and the problem at the time was even there were discussion if it was necessary to introduce some social distancing rules, some social distancing measures, what would be the effect. So of course that debate is sort of over now. So the debate is more on the when we can lift the measure, pretty much all over the world. So it may sound a little bit outdated, but let's say the general idea probably is something worth discussing, I hope, and we are trying to work to extend this model to include the problem or the question of how and when to lift the measures. So I'm happy to take questions along the way. So it's a short paper, so there is plenty of room for interaction. So as many other economists, we jump on this idea of integrating macro models with epidemiologic models. So the most popular that economists immediately start to adopt is this SIR, which is susceptible, infected, and removed. And as the more I read, the more variants on this type of model I discover. One paper that got lots of citation in the last month is this Eichenbaum and others, which is basically sort of the SG general equilibrium model with an epidemiology aspect, which is basically motivated from SIR. And one of the first papers that got some influence is this paper by Anderson et al. By the Imperial College, and was published on Lancet, which is the leading world medical journal. So of course they stress the role of non-pharmaceutical intervention, because pharmaceutical interventions are still not possible, they are not available at this stage. So they say we need to stress the role of social distancing in particular. The problem connected to that is a problem that is strictly behavioral for economists. So how do we convince people to social distance in a democracy? If we're not a democracy, it's a bit easier. In a democracy, we need to convince people that social distancing is the way to go. So how do we convince people? There are, of course, important behavioral implications in that. So we thought about adapting our previous works on behavioral macro in a sort of epidemiological model, which is a simplification of SIR because, as you will see, we don't have the removed. So we have only susceptible and infected. We are working on the removal. I will talk maybe at the end about that. But the thing that we consider is paramount is the fact that there is very little information. So the information that we have is typically incomplete. It is not immediately available, and it's not accurate because, for example, if you look at the number of infected people, or number of confirmed cases, pretty much everywhere, maybe a little bit less in Australia, but this number is much less than the actual number of infected people due to the fact that there is a bias in testing. So using the standard paradigm of perfect information, the standard approach in the SG, for us it didn't sound quite right. So imperfect information is the setting to use in this kind of situation. If we use imperfect information, a very popular approach is a discrete choice. McFadden is the father that won the Nobel Prize in 2001. And then there are a number of applications. So I cite here a couple of them, Rock Holmes and Thomas Lux. And the applications, many of them, especially in the 90s, early 2000s, were in finance. And then they were extended later on in macro and other fields. So what we have tried to do was to try to estimate, given the fact that there is imperfect information, given the fact that people basically have some uncertainty in the decision, and this can create delay in which the effects actually take place. We tested what can be the difference in implementing, for example, late measures, but stronger measures, or implementing early and milder measures. So basically, we wanted to assess jointly the timing and the extent of the measures, considering the behavioral aspects. So, and the rest is pretty much a standard discrete choice model. So the discrete choices in this case are between social distancing or not. We consider a large population equal to M, and we consider that people enact social distancing practices, choose D, and the share of them is given by S, small s. And then we define the growth in the confirmed number of cases and the standard growth. So the rate of growth would be equal to some positive number alpha. And then there is an impact of social distancing practices, which is quantified by D. This impact is, of course, changing over time. And it has the effect of reducing the growth rate in the number of confirmed cases. With the clarification that D cannot be bigger than alpha, so we don't consider, of course, that people heal because of social distancing. So we focus on the cumulative number of cases, and this cumulative number of cases, the growth can be reduced by social distance. How this reduction in growth takes place? So we consider a number of factors. So first of all, as I said, we don't consider, we consider only the total number of cases, so we don't consider the removed cases in SIR, so it's not really an SIR. What we use, and we don't consider so that the people basically exit from the population due to healing or death. Now we are trying to expand this. There is the issue, of course, if people that are healed are susceptible, so if people acquire immunity by being sick or not, which is still a matter of debate, so we didn't want to go there at the stage. Then the second assumption is that as long as people enact social distancing, there is an effect on the rate of infection. So as long as there is some social distancing, the rate of infection is decreasing. And then we consider that only social distancing is effective. So it's the only measure on which we focus. So using these assumptions, we can define equation 2, in which we see that so dt, let me remind, is the effect of social distancing on the growth rate of the pandemic. So this impact is growing in time depending on S, which is the share of people who actually are social distancing, multiplied by a fixed parameter, which is beta. Okay, so the more people enact social distancing, the more the infection rate is decreased, and this depends on some constant.
Corrado, can I have a question?
Sure.
So I think people's choice might respond to the observation in terms of the number of cases in the society. So they will respond to prevalence, right? So, and my question is that in this model, do you allow them to respond to the new cases, so in other words, the incidence, or to react to the prevalence, which has to do with the all the numbers that have been recorded, but some may actually recover. But every time we see the news, the numbers you get, you have the total of cases accumulated over time. You also have the cases that are the new cases every day. So I'm curious, what kind of information is more relevant for people to respond to in order to change their behavior?
Thank you, Simon. So I'm going to talk in a bit about how we model D, so how we model S, how we model social distancing. And people, they will consider the expectation in the growth in the number of cases. So maybe we can go back to this in a few slides. Because at the moment, I'm not, so in the first part, we don't model how basically S is determined, so the decision process, modeling in the second part. So yeah, maybe I should have said that earlier on, so thank you for pointing this out.
Yeah.
So at the moment we just model the interaction between the growth in the number of cases and the effect of social distance. And then I will talk about how basically D is determined, depending on the choice of people. Or S is determined, sorry. So maybe we can go back later if it, maybe it's more relevant later on the question. Basically, looking at China, there was no choice. So we just estimated, at the time was also the only country in which there were some measures in place for a time long enough to get some estimation. So what we do, we consider beta ST as a constant. So considering that there is the fixed number, fixed share of people that immediately after the enactment of the measures decided to social distance. And then we estimate the other parts, trying to fit. Sorry, there is some traffic outside. I hope it's not too much. We estimate the other parameters to fit this S-shape growth in the number of cases in China. So what we did was to basically, after, no, I don't remember, okay, so after 14 days, there were measures, after 14 days from the first cases in Wuhan, measures were enacted. So we consider that from day 14, there was this factor, beta ST, of reduction of effectiveness of social distancing, so of reduction of the infection rate. Now we introduce social distancing. So in order to introduce social distancing, we consider that all the confirmed cases social distance themselves, and the rest of the population decide whether to social distance or not. And the probability of choosing the option of social distancing is given by PD. And now we discuss how people decide. So in discrete choice theory, I don't know if you're familiar with that, people have sort of random utility function, which there is a deterministic component that is given by observable quantities, and then there is a random component which basically depends on unobservable factors that are related to the heterogeneity of individuals, so different tastes, different type of personal biases, and so on. So the utility function is expressed by 4, so we have the deterministic component, so data that are available for both the decision maker and the researcher, which is the number of confirmed cases, or better, the expected growth in the number of confirmed cases, H, and then a cost of choosing with. So of course there are costs in social distancing, there are economic costs, because businesses need to shut down, and there are welfare costs because we don't benefit from social life, social activity. And we use this C as the policy variable. So
sorry, can I have a clarification?
Yeah.
Because you kind of mix up this social distancing, which I think should be the individual choice, but you mix up with other lockdown, which, you don't really have a choice. Are they the same thing, really?
Not really. So I guess you might be right on that. I mean, of course, in the decision of individuals, we have both people who are constrained and people who are not. So this is sort of average between the two. But you're right, we should have, for a more accurate modeling, maybe we should have some sort of business, or let's say a minimum increase in cost.
Related to that,
We don't capture, short answer is that we don't capture that, yeah.
Related to that, when you fit in your model on Chinese data, China, there was no choice per se, right? After 14 days, they all went into lockdown. It was state imposed.
Yeah, that's what we assume, yeah.
So then basically the model is giving the choice, but the data is not aligned for the choice.
No, so what we did was to use China to estimate the parameters.
Okay, makes sense.
So as I will mention later, we consider that 0.9 of people were social distancing in China. There are people that cannot social distance due to work, for example. So we consider, okay, let's say 90% of people social distance, so that allowed us to estimate the parameters. So yeah, we consider the choice with the caveat that Simon pointed out. And we use C as basically the cost of social distancing. So the intervention of the government consists in lowering the cost of social distancing, so make social distancing more likely. And epsilon represents all these idiosyncratic and observable factors that in discrete choice theory are modeled as a random component because they are not under the direct observation of the researcher. Gamma is what we normally call intensive choice, which is the weight of the deterministic component. So basically the higher is the weight of the deterministic component, the more rational individuals are, so the higher is the weight of the observable factors, or lower is the uncertainty about the decision of people. So using the results that are common in this literature, so we use Train 2003, if the utility function that we calculate in 4 is positive, people decide to social distance, otherwise they choose not to social distance. And assuming that the idiosyncratic factor, the random factor epsilon, is logistically distributed, we can express the probability of social distancing as in 6, which is a standard type of result in this literature. So we have this type of exponential distribution. Now we still need to model expectations because people have a guess, educated guess maybe about the growth in expectation, the growth in cases, but they don't have the full knowledge on that. So we assume that people update their belief about the effect of social distancing according to 7, where tilde D is the expectation of the previous period, D2 minus 1. So they sort of update their process according to 7. Because, of course, they cannot observe all the important variables in this decision. So then we calculate the model alpha, which is the growth rate, if you remember the first equation, for the number of confirmed cases.
Yeah, sorry, I hate to interrupt again.
No, that's okay.
So I guess it's the previous slides kind of answer my previous question. So here, basically, you are imposing an assumption that people's behavior respond to the new cases or expected new cases.
Yeah, here.
So it's not about the existing, so it's the expectation between HT plus 1 minus HT. So that's just the new cases. And how do you expect that to change over time, right? So in epidemiology, they would also think about the prevalence in a sense that it's total number of active cases, not just that the daily changes. So I don't know, what's your take on this? Which one is, is more sensible?
So we just wanted to keep things simple because of what I was saying initially, that there is uncertainty about this remove factor because it's not sure yet how much immune people are once they heal. So are they removed? So because in typical SIR, once you're removed, you cannot re-enter the population of infected people. Okay, if people die, that's for sure, that's a number which there's no doubt about. But in this standard SIR, removed people do not re-enter the susceptible subset because they develop immunity. And especially 1 month ago or more when we were working on this, we weren't sure about that. So there were not really data that still a bit controversial, so which is the rate of healing of people. In terms of behavioral perspective, I agree with you. It probably goes with phases. I mean, I can see personally, initially I was scared about the growth. Now I'm looking at the active cases. So maybe after the peak, people start looking at active cases. But that's very, sort of anecdotal type of take. What do you think? I'm curious.
If I'm thinking about what's the chance that I might contract the disease, then the relevant number should be those active cases, right? Because that's the number that determines the chance that I might get disease, right? It's not just the daily new growth, but also who are still infectious would go into my decision.
Yeah. And this is something that we are sort of considering now in the extension, because now we need to include anyway the remove. But yeah, I think probably also depends on proportion, because initially probably the proportion of people that are healed is relatively small yet, so it doesn't impact the perception of you, not to the extent that it does later on. So going back to the calibration, so we consider, as I said, that in China, 90% of people social distance, so that allows us to estimate beta, which is basically the impact of social distancing on the reduction of the infectiveness, the spread of the virus. And then the other parameters, we simply calibrated them, the other two parameters, so the intensity of choice and the updating rule for people's belief about the effectiveness of social distancing. And the initial condition, we use the proportion of infected people in Wuhan when the first cases were initially recorded, and all the other variables were set to 0. So we did some simple simulations, so probably you saw many of these graphs by now. What we see here is that, so we started with C, so the cost of social distancing equal to 0.5. And then in the blue line, we introduce a reduction, the cost of social distancing, so what we call the policy intervention. And in the top panel, we see the total number of cases, and in the bottom panel is the growth. So it's quite clear that there is a massive impact of this reduction in the cost of social distancing. And it looks like the important thing is just to enact measures. The size of the measures seems to be of secondary importance. So the big reduction is the fact that measures are enacted. And then one effect besides of course, the reduction in growth is that the point in which the growth in cases is equal to 0 is much earlier in case of intervention. So we see that roughly around 60 days when there is an intervention, the rate of growth goes to 0. And looking at the sort of micro aspect of that, so we can focus on S, which is the number of people social distancing. And the dashed line is the intervention date. So we see that people social distance themselves even before there is a measure by the government. And initially when we saw this, we weren't so happy. But we were vindicated later on when the first data about social distancing in the UK were available, and they showed that people started social distancing before there was an announcement of measures by the government. So in a way, it does make sense to have this type of dynamics. And then, of course, here the fact that we don't have the removed is evident in the sense that people keep social distancing, so there's no relaxation even when the rate of growth decreases, because of course people look at the total number of cases. So I'll show you later on, if you want to look at the when to lift measures, this model is probably not so suitable. Then we run some sensitivity.
Sorry, Corrado, can you tell, I missed this part, that people reacted before the measures were enacted or before official lockdowns were announced?
Yeah.
Where do I see this, that they reacted before that?
You see here, so you see that S departs from 0 before the measures are enacted. So the measures are enacted where the dashed line is, which is period 7. And you see that before period 7 there is already growth. Then of course the steepness of the growthiness is different after that.
Okay, thank you.
Can I ask a quick question?
Sure.
So basically your trajectories will depend crucially on when the lockdown is implemented, isn't it? So the difference that you're showing between the black line and the blue line, well, that difference could be really, really small if suppose the lockdown comes in later, right?
So I have maybe what I was presenting now, this looks at the total number of cases and the time of intervention.
That's what I want.
The later is the intervention, the higher is the total number of cases. Is that what you were asking?
Exactly, yeah. Oh, thanks for that.
Okay. If you need more clarification on that. Okay. And so this is, we see that, of course, H is growing in PI. The other two lines are the relative to the intensity of intervention. So the blue line is a stronger intervention and the red is the strongest. We see that basically it's increasing in all three of them. It seems to be, so timing seems to be more important, especially if you look at this other graph, in which we have the total number of cases as a function of the strength of the intervention. So of course, the more we are on the right, the milder is the intervention, because milder is a reduction in cost. So we see that basically the timing, and we have three lines for different timing. So the red line is the latest intervention, and the black is the earliest. So the timing dominates the intensity. So the earlier is the intervention, even if it's milder, it is more successful than a late intervention that is stronger. And here we have another visualization of this. So the black line is early intervention and mild, and is later intervention with the stronger, to a stronger extent, a larger extent. And we see that there is quite a difference, and the difference also is visible around the time when the infection basically dies out. So from this simple analysis, we can say that timing is more important than how much you can convince people. So the earlier you act, the less work you need to do to convince people to social distance. So here we did some very basic numerical experiments. So for example, implementation day 10 rather than day 5 more than doubles the final total number of cases. So in this type of process, I mean, it's not maybe striking this type of process, of course, the timing of the intervention is paramount. And basically you cannot catch up with a stronger intervention later on. So we wanted to stress, first of all, we wanted to stress the role of individual choices. So in a way, applying a SIR model in this type of context, in this situation, requires to look at individual choices. Both because, of course, they determine an effect in the velocity of the spread of the contagion, and also because there is a time delay between when people started following some sanitary rules and non-pharmaceutical rules and when the effects are apparent. As I say, timing is relevant, and something that basically sets us a bit apart from much of the literature that has been produced in this month, couple of months, is the role of uncertainty. So, of course, there are limits that, I mean, I didn't shy away from the limits that we have in this first installment of the model, but we believe that this type of approach in which uncertainty can be included in the decision process of individual maybe is a better answer at this stage compared to standard general equilibrium model in which individuals make optimization in conditions that maybe are not exactly what we are facing right now. Also considering something that immediately came to our mind is the effect of mass testing. So mass testing has the effect of reducing uncertainty, because in countries, you know, I don't want to make names, but in some countries, I mean, I can tell my country, Italy, testing was still, in recent times, much lower than what it should be. And these have created lots of problems, but also lots of uncertainty about the effectiveness of measures, how to implement, and how effective they were. So mass testing not only push infected people to isolate, but also reduce uncertainty. So from a behavioral point of view, there is a secondary contribution that is also very relevant. So I was saying about lifting the measures. So as I said, we are developing a different model. I don't have a simulation, so I was hoping to have something to show you, but we don't at this stage. So I just did some experiments with the model that I presented. What I tried to do was to reduce, draw the measure at some stages. So we drew the measure at the 60th day. So what we see, what I wanted to see if there was the chance of a so-called second wave. So what we see from this very simple experiment is that there's no second wave. So people started very slowly withdrawing from social distancing. Of course, there is a limited, we pointed out in the discussion with Simon that we should consider the active cases at this stage probably as a more accurate measure of how people make a decision. But it seems that in the case that we saw with the very early intervention on day 7, there's no chance of a second wave. I didn't have time to see when the second wave actually can start, so for a late interventions, like let's say what happened in the UK or in the US, if there is a chance of generating a second wave. But from some simple experiments that I did in the last few days with this model, there were no generation of a second wave. But of course, this is probably not the best model to test that we need to extend. And that's pretty much all I have to say. Say that the paper was short, so there's not much else. So I'm happy to take any comment and suggestion.
Thank you, Corrado. Touche, go ahead.
Okay, thank you. So one question is the sheer act of a government imposing a lockdown might contain information, right? So if I'm not certain about what's the rate of prevalence in the population, but the government says, oh, this is serious, and that's why we're imposing a lockdown, I would use that as information. So basically, what that'll imply is the model on the left-hand side of the imposition cutoff, and the right-hand side would be very different in terms of how I update my information. So
would strengthen in a way.
But it could strengthen, but it could also, well, I was curious as to whether it can weaken it or not, but something to consider, right? I mean, perhaps have an extra parameter in your information updating function, which turns on the moment the government imposes the lockdown.
So lockdown is sort of signal.
Signaling.
To people.
I think Ken has a question as well.
Yeah, Ken.
Yes. It seems that these data that we look at every day, or sometimes multiple times a day, might well be contaminated by measurement error, because we've got a number of new cases, a number of active cases, and then the integral of all that, the stock of all past cases. Now, if that's true, it probably means that you should focus on some data rather than others. Now, can we look at your graph for China that we started off with, please? Because that was very instructive. It was about slide 2, or yeah, that one there. So if we look at round about day 34 or 35, the red line, which is actual, it's horizontal. Nothing happens. So, but then thereafter, there's a huge jump. So it seems that one interpretation is that there was underreporting in day 34, and then on day 35 they had a catch-up. So that probably means that, you know, these errors tend to wash out with the aggregate, so that you might want to put more of your money on the stock rather than the flow, the day-by-day flow, or the or the half-day by half-day flow. Now, you understand why this would happen. If we're dealing with emergency rooms, you know, doctors are harassed, and sometimes they don't write down the actual time of the event and what happens this day, maybe recorded as the next day, change over a shift and all that sort of stuff. So that's why I say I think measurement error is possibly important in all of this, especially with respect to what do people actually look at? What do they, or what should they pay attention to? An issue raised by Simon.
No, I totally agree. I mean, for what we saw in the data, that clearly there is something that doesn't quite square. There is something that is reflected what I call uncertainty, but especially, I mean, another country that is emblematic on that is Italy, because the number of positive cases and the number of deaths per number of cases are sort of outliers compared to the other countries. So it means that there is some bias, probably due to testing. I don't know, maybe under some cases, but that's totally true. But that's still, in terms of behavioral perspective, is we can only look at the number of confirmed cases, so what the media tell us. Because we had a discussion on that, but basically the only information that we have as citizen is the information from the authority about the confirmed cases. As biased as it is, as imperfect as it can be.
Well, it's the volatility of that rather than the bias, because, you know, under and over reporting probably washes out over the longer term. So some measure of the relative volatility of that, or the measurement error component of the volatility, might be able to extract that, make some assumptions about it. You do at least do some sort of smoothing of these big jumps, or these lack of anything happening, these horizontal. So you can see horizontal segments elsewhere in this curve.
Yeah, there were a few days without, 2 or 3 days without increase. I remember that when we were looking up. And then it spikes up.
Yeah.
But I mean, it's totally true from a researcher point of view. So from the person who analyzes the data, as a decision maker, you see the data day by day. You make your decision day by day. So you don't observe the volatility in real time. In a way, you need to look back. And then, okay, later on, of course, it can undermine your trust in the data as a decision maker. Yeah.
Thank you.
So that's a question. Are you done there, Ken, with your question?
Yeah, sure. Thanks.
Great. Thanks, Corrado. It's an interesting presentation. I was just chatting with my mother the other day, and she was saying that she thinks that this pandemic will actually lead to sort of longer term sort of behavioural changes. So, and there is some evidence, I think, in the literature that sort of big time shocks like this can actually, change preferences and behaviours. But I'm just thinking, with your, the utility model underlying, the utility maximisation model underlying your model here, whether that takes that into account, because I presume these things are considered fixed and sort of exogenous, so whether or not, I don't know, you can allow for that, I guess, so for changing preferences and behaviours over time.
I don't see now that in this function. So what we were discussing initially was whether to introduce herding in that. So I social distance if more people social distance. Then for a number of reasons we decided not to do it, so to keep it as simple as possible. That may be, I don't know, that may be captured by the persistence over time. So what we see here maybe is a bit gross now, is a bit rough as a measure. The fact that social distancing doesn't decrease. But maybe extending the model is something worth to consider. I mean, for sure, I'm not sure when we go out and hug a friend again. But for an Italian, it's a big thing, as you can imagine.
Yes, I think Simon's got a question. Thanks, Corrado.
Thank you.
Yes. So there's a new working paper came out last month, the MBER working paper by Fabudi, Jarosh, and Shima. I'm not sure you're aware about that one. And they also look at the social distancing. And also they apply the SIR model to analyze people's behavior in terms of the social distancing. And so I think the two main things coming out of that paper is that first, they notice that people already start practicing social distancing way before the government start to impose any intervention. Okay, simply people, they heard about the news and then they start to react to it, even without government intervention. And then the second one that I think that might find it most striking is that their policy suggestion is that the government should keep social distancing in place for a very, very long time until a treatment is found. Okay, so my take about this and think about it related to your model, I think one reason that you find that the people change behavior very little or just a little bit afterwards is probably because you only allow people to respond to the growth rate of the cases. But think about that, suppose that you come to a steady state, there's normal growth rate. But people still have this fear in mind because they realize that there's still no vaccination, there's still no treatment. And simply because there's no new cases every day doesn't mean that the threat or the risk is gone. So I guess that component is not capturing your model, and that part is not reflected.
So some sort of persistence, what we were thinking just a minute ago.
And a related point that you, I think, alluded to is the herding behavior. Well, I mean, wouldn't it be the case that if there's quite a bit of herding and people place a good amount of weight to what other people have been doing, then there'll be a cascading that starts after a point, where people might just ignore the individual signals or the growth rate, what Simon was suggesting, the growth rate on the daily basis, but just do it because everyone else is doing it. Right? So
it's typical when you introduce herding, you have typically very high non-linearities.
True. But I'm thinking more than herding, it's more about cascading, like after a point, I just ignore my personal information, I just go by what the behavior of everyone else is telling me. So maybe something to think about in terms of
so behavioral cascade, not so much informational, but sort of behavioral cascade.
And that's specifically important because you're talking about the information being imperfect, and cascading is so common when you know that your information is imperfect.
We have three more, or Emiliano wants to ask a question or make a comment, and also Frank Leo. Maybe first Emiliano and then Frank.
Yes, hi. I was thinking about the effect of mass testing, because what we're observing, the number of cases or the first difference of the number of cases is a conditional probability on the sample size that you are taking out of the population. If we go and do mass testing, so we increase the sample size, we are likely going to pick up more cases and more new cases. One challenge that you push forward is that, okay, that is going to reduce uncertainty, and then it will make people more active towards social distancing. But it could also work in the other way, because I was thinking, okay, we increase mass testing, we increase sample size, we have new cases. I'm doing social distancing, I'm seeing that the cases are going up, so what am I going to bother doing social distancing? So I think it could work. Mass testing could signal the opposite, make people think that social distancing does not work.
I think that could happen if all of a sudden they increase the number of testing. Then you would have a spike. That's probably what happened in Wuhan, in China. Then you have a spike. But if they do, like my understanding in Australia, they increase quite constantly over time. So we didn't observe this spike indeed. So
there was actually there was a day, I don't know if I'll bring it up on the ABC website, where there was they increased testing in New South Wales in the space of one day from 6,000 tests to 12,000 tests in one day. And there was actually a huge spike in the number of reported cases. But I think that was sort of reported in the media. And you can see on the distribution, you can still see that there's a massive spike in the daily distributions. But people were sort of informed about it more or less. And I think it was when you do see a sort of sudden increase in testing, I think people know about it, so it's maybe not quite so likely.
That's precisely my point. The key aspect here is how do we model those expectations. You're assuming that people know about that, and we are thinking about one country. But something I've seen, for instance, I'm from Argentina. In the media now, one of the topics is why Argentina has less cases than Chile. And one of the main differences is because Chile is doing mass testing while Argentina is not. And there is some debate about that. The same applies to Finland and Sweden. So it's true that for a person that is in New South Wales, they might be looking at the New South Wales cases, but then they are thinking, okay, I'm doing this social distancing, and Finland is not doing social distancing, and they have less cases, so why am I bother doing this?
Sure, yeah. Yeah, I think, a lot of these things can work both ways. I was thinking, there's almost a moral hazard. I'm not proud of this, but sort of looking at my own behavior, there's almost been kind of a moral hazard thing where I sort of really stopped bothering with a lot of social distancing just because I can see that everyone else is doing it and it's been effective. And so I look at sort of the marginal contribution to my own behavior, and it's 1 in 2 million. It seems like everyone else is doing the work for me, so I'm being very lazy. I mean, that's kind of not so much related to the sampling issue, but just in general. yeah, a
No,
lot
I
of
think there can be some moral hazard, of course.
Frank?
Hi, Corrado. Thank you for an interesting
Hi.
presentation. I mean, to be honest, I haven't read your paper, so my question maybe may sound stupid. My question is related to your second last slide regarding your contribution. Let me go with you here. About the intervention, time of intervention. So you probably have already time of intervention. Maybe the second point, the second policy indication.
The one about uncertainty.
Maybe you can just go to figure two. Yeah, that's right. I mean, my question is related to time of intervention. So I'm pretty sure you have incorporated that in your modeling, but I guess I just wondering how the mechanism works. Let's just say if you have two countries, country A has a initial age being 4 times 10 to the power -5 or -4, and then they'll say they'll intervention comes in day 5, and comparing to another country where have a slightly initial higher age, but have a marked intervention being on day 2, for example, would they present a similar trajectory after the intervention? So I guess my point here is that let's just say that if they sign with different age, holding everything else constant, like would they present a similar trajectory after the marked intervention?
So you mean the relevance of the initial conditions?
Yeah.
Yeah, we tried, because initially we tried a bit randomly, and there was not much change. Of course, within a certain range, then if you start taking very high numbers, something changes. But the shape and the type of reduction is pretty much consistent for different initial conditions.
I mean, I guess that can be I don't know, first policy indication, because let's just say, if back in March, if other governments trying to learn from this, and of course, every country started with different age, right? Some countries had a high age, like in, for example, in Wuhan, where I am at the moment. But so which means that, let's say, like for another country, want to learn from this experience. So does your model suggest that as long as they have a similar age level to start with, and they have a similar, if they can cut the marketing intervention day a lot earlier, they would have a very similar trajectory after that?
Yeah.
All right, cool.
Yeah, in the sense that, yeah, I mean, that's, so the timing is basically the dominating variable, regardless of the initial conditions. Of course, if the rate of growth is different, so what we call alpha here.
But rate of growth is not time varying, right?
And no, we estimated like a constant rate of growth here. Like we thought about that more as a sort of biological type of variable. So how infective is the virus? That's why we say, okay, that doesn't change. What changes is the fact that people have less contact, so it spread less fast, but the biological characteristics of the virus do not change. So that's why we kept alpha as a constant.
Okay. Thank you.
I don't know if I answered, did I understand your question right?
I will read it more. Thank you.
Thank you.
Right, you said Italy is an outlier. That's what you said earlier. And is it really an outlier, or is it just the behavior?
No. I mean, because if you look at, for example, the death rate in Italy is much higher than, for example, Germany or Australia, but like 3 or 4 orders of magnitude higher.
Yeah, and why is that in your opinion? Just because we were hit earlier?
I mean, from what I read, it seems that in Italy it was under testing. So people died. There were afterward they say it was COVID, but they were not tested initially.
But wasn't that also because of the age profile? I mean, so most of the deaths happening in the south.
Yeah, but from what I understand, it's not enough to explain that. So there is not like so much different from Germany. It is different. So Italy in terms of demography is like the second oldest country after Japan in the OECD area. So that plays a role definitely. But from what I understand, it's not enough.
Are Italian, I mean, is there, because you talked about behavior as well, right? And your paper's about social distancing. And I think you mentioned that earlier, that Italians, they do a lot of hugging and kissing on the cheeks and all that, right? I mean, is it possible that there was this you have this very different social behavior, that this also led to a faster spread of the virus? And is that linked to your paper somehow? And that, well, Japan is doing pretty well, I think. Australia as well. There are outliers on the other side of the spectrum.
I don't know, maybe the fact that there is something like that. Australians are more law-abiding than Italians. So if the government in Australia said, do that, people are more likely to follow the indications rather than they do in Italy. And also in Italy, the largest spread was in the north, where the density of population is much higher. So I don't know if this habit, this Latino sort of habit, was so important at the end. Because I mean, if we are in the same room, we can get infected even if we don't touch each other. So I'm not sure let's say the physicality of Italians actually had a role. But that's a hunch.
Any final comment, question? I don't see any hands up. If not, I'm waiting. There's a hand. Frank has another hand. Is that another hand there, Frank?
That is the clapping hand, sorry.
Okay.
Thank you.
All right, so thank you everyone for attending. Thank you for Corrado for presenting. I think for me that was very stimulating. I think it's good to think about these things. There's I guess a lot of opportunities to do research in that field.
Thank you for the comments. Thank you for the comments.
Thank you, Corrado. I also do that.
Thank you, Corrado. Thank you.
Thank you.
Yeah.
Hope to see you live.